Alright, welcome again. Today we'll talk about the reduction of a simple distributed load. This section is 4.9 from the textbook. So distributed load means force distributed over a surface or over a line. There is distributed force could be over length, and we call it force per unit length, or force per unit surface. So the first term has a unit of Newton per meter. The second term has a unit of Newton per meter square, which is a unit of pressure. Example of load per unit length is this distributed force, which is acting on a cantilever beam, a beam that has a free end and fixed at one end. And the load is exponentially or parabolically increasing with the function W of x equal 60x squared Newton per meter. So where x is measured from O. So this is our weight per unit length, and that's our x measured from here. So simply you substitute the length and the x to obtain the amount of force at that particular point. For example, find force per unit length at x equal to, let's say, 0.5. Simply W at x equal to 0.5 is equal 60 multiplied by 0.5 square. This is Newton per meter. This value is at 0.5. Now, if someone asks you what is the total weight acting on the entire cantilever from 0 until L, saying that, or assuming that the total length of the cantilever is L, how much is the total weight? We know from the calculus is that the total area is the integration under the curve, and the total weight is the area under the curve. Therefore, the total weight is the integration from x equal to 0 until x equal to n of x, or W of x dx. So this is called the integration, and I hope all of you have taken and know the integration. So in this lecture, I'm not going to go through integration fundamentals, but I will indicate a few examples of simple integration. Let's take this example. Find the total force acting on the beam. This is simply supported beam, and there is a uniform load given by a constant magnitude 5 Newton per meter. So imagine this is a continuous blocks at a certain height with a given constant density. So the force per unit length is constant 5 Newton per meter. So we want to find the total weight acting on this beam, regardless where it is located at. That we will discuss later. So from the discussion we had, the total weight is the area under the curve. This is a rectangle. So it's a W naught multiplied by L, and that's equal, W naught is 5 by 2, and the unit is 10 Newton. So this is Newton per meter, so we end up with Newton. The question is, well, we represented this distributed load with a single load, so this is an equivalent system, and we know that the total weight or total load is simply the area under the curve, 10. Now, where should that be located? From point O, and we denote that by x bar to indicate the location. What is this value, right? Well, by inspection, for now, you will conclude that the location of this WT must be at the center of the rectangle. So therefore, X bar is equal, and this is by intuition and by logic and common sense, 2 over 2, which is 1, where 2 is the length of the rectangle and 2 is the center of that length, which is half of it. So this is 1 meter. Now we will introduce a much more systematic method of calculating the centroid, what we call the center or centroid or location of the effective weight or total weight using method of moment. Now the topic is a more generalized method, is how to find the location of the resultant forces. Consider that we have a distributed load, random one, but we know the function of it, which is W of x, which W of x is again is the force per unit length, is acting on a structure. We chose here a 2-pinned or simply supported beam. The load is expressed as a function of x, where x is measured from a point O, and this is the x direction, right? The total length of the beam is L, and we learned how to find the equivalent total force or resultant force, WT, by simply saying that this is the area under this curve, which is the integration from 0 to L W of x dx, or the area under the curve. If the area is simple, then you just geometrically calculate the area. So previously we said that this WT, right, it represents the resultant force, and its location by intuition for a rectangular was centroid or center of that shape. Now for a general force that we don't know, or if it's complicated, it's located somewhere along the x-axis, and we do know that by the centroid x bar. This is not a vector, this is x bar. It's not a vector, it's an x bar c, sub c. Now we want to find this x bar c, where it is at, right? Previously from sections 4.6, when we talked about system and equivalent system, we said for two systems to be equivalent, not only the WT must be equal, right? Because this and that, both these forces are equal to each other, because WT is the resultant of this line force. But also we want to verify another condition, which is the effect of the moment of the equivalent resultant force must be similar to the moment produced by this distributed load. In another way, if I were to first have to calculate the moment of each individual fragment, right? Each individual fragment here. And the moment I choose to calculate that moment from W. So it's simply, if I discretize this profile into an infinite number of rectangles, and want to calculate the moment of each fragment about O, it's simply the summation of the of x, which is the location of that fragment, multiplied by its value. And supposedly we say that the value is small, or the delta x is small. So it's x wx. Now if I want to reduce this into a much more understandable, so instead of summing a very small finite number of fragments, I can represent that in integration and say that the total moment produced by this distributed load, it's simply the integration of 0 to L x wx dx, right? And that will give me the moment, total moment of this distributed load. On the other hand, we know for the equivalent system, this is, let's say, system B, which is equivalent of, we want to both system A and system B to be equivalent. To calculate the moment of that WT, we just simply, in scalar form, and this is, since this is a single load, this is a single load problem, right? We multiply the distance, the orthogonal distance, which is xc bar, which is, remember, d, multiplied by the WT, right? So for both systems to be equivalent, for the equivalency, the following has to be met. These two values must be equal, meaning that x bar c WT must be equal to summation of all the fragment, which is the integration x wx dx, right? So I can now find xc bar, which is 1 over WT equal to 0 Lx W of x dx, where, and this is multiplication, where WT is simply the area under the curve. So in the textbook you have, it's represented also by 0 to L x W of x dx over integration from 0 to L W of x dx. I don't want you to get surprised by this formula. They are very easy, and we'll take some examples to follow. So this is from the presentation, which is already posted. Only take simple examples that include shapes of rectangle and triangle, right? And we'll, instead of, I don't want you to do the integration because I don't think you are ready to take the integration, but we'll show you how to use it, and also we'll memorize how to calculate or how to find the centroid of a rectangle, which we said it's a center, and also of a triangle, and a combination of both. Let's take this example. This is the centroid of a rectangle. As we promised, we will show you how to calculate that using the integration, and then we'll memorize the formula and use it forward. And we'll take a combination of both rectangle and triangle. So we have distributed load, uniform, called the uniform distributed load. It has a rectangle shape with a height W naught, acting on a cantilever beam or any beam. The total length is L. We want to find the equivalent system that has a total resultant force, which is the integration of the unit force per unit length over the length, which is area under the curve, which is simply W naught multiplied by L, right? And the XC, the location to satisfy the moment equivalency, which is from the formula before, it's x W naught, well, W naught is W of x dx over the area under the curve. So this is, anyway, this is WT, right, which we have it here. So XC simply is integration of W naught goes outside of the integration x dx over here W naught multiplied by L. These cancel each other. Now from the calculus, integration of x is half x squared, and you substitute from 0 to L, and this is equal 1 over 2L L squared minus 0, and this is equal to L over 2. So that's simply, this is your x bar. So it's half, as we said, it's half. So in conclusion, for rectangular shape, you have the total is simply W multiplied by the length, and location is simply L over 2. So this is what I wanted to memorize for rectangle. let's take this centroid of a triangle. We have a ramp distributed load increasing from 0, 0 until a final value W naught at a length of L, which this ramp is a linear system and described, let's say, by function, and that function is x multiplied by W naught over L, and we want to find first the total force, which is, we set the area under the curve or under the function, which is area of triangle, which is half base height, so it's a half length multiplied by the maximum value W naught, and then this is gonna give us total resultant force WT, which is half L W naught. Its location is somewhere here. We want to find out how much is that. We said we will use the moment equation to make sure that the centroid or the location provide an effective feeling or an effective equivalency. So xc is equal to the integration from 0 to L xwx dx over the total, where you know the x is given to us by xw naught over L. So we want to calculate this term, right? That's what we want to calculate. Again, what we want to find is the formula, and then we'll be using it. But this is for your note, because in later chapters we'll be doing or conducting the integration. We'll be using it. So I will encourage you, if you have taken the class or calculus, to revisit that. If you're still working on it, by the time that we reach chapters, advanced chapters, hopefully you will be able to conduct integration. If you haven't taken it, it's still okay. We are taking simple problems, and my point here is to show you how to do it. And it doesn't matter whether you know it or not. For now, you're gonna rely on the result of this. So x prime, the location is simply, so I'm just gonna plug in 0 to L, x wx is that multiplied by x. This is not dot, this is just simple multiplication, multiplied by W naught over L dx. All of that is half L W naught, right? So constants goes out of the integration, as you know. So this is gonna be W naught over L, and this is gonna be L square W naught, right? And 2 goes up over here, and we are left with x square dx from 0 to L. So what's the integration of that? Use the power rule. So we are ending up with the following: 2 over L square multiplied, integration of this is 1 over 3 x to the power 3, substitution from 0 to L, and that is equal to 2 over 3 1 over L square, right, multiplied by L to the power 3, and that's equal to, so this is what I wanted to memorize, 2 over 3 multiplied by L. So for the triangle, that the location measured from O, from here, is 2 over 3 over L. So it's like that. From here to somewhere here is 2 over 3 L. So what's left? If you want to measure it from here, this is 1 over 3, right? 1 over 3, 1 over 3 L. Alright, so make sure that you guys see it. Okay, we'll take example that involves both rectangle and triangle combined and see how we calculate. Let's take a look at this example from the presentation file, and then we'll conclude the lecture. We are given a combined distributed load comprised of two profiles. One is from 0, let's say from here, from 0, 0 to 6 feet. It's a triangle shape. And then from 6 feet to 8 feet, it's a uniform shape, rectangle. And the values are given. So the maximum value for the rectangle is 150, and it's here it's 150, the maximum value for the triangle. We want to find first the equivalent force and the location of that equivalent force from point A. So first we need to calculate the total force. The total force is the total area of this curve, which you can break it down into the area of rectangle and area of triangle. So the area of triangle is simply half 6 multiplied by the height 150. That's going to give you the resultant force of the triangle combined with or plus the area of the rectangle, which is 8 multiplied by 150. So the total force, resultant force, is combining these two areas, which is going to give us 450 plus 1200. That's the total. Now the question is, where is that located at? Where is that located at? Right? Now there's two steps. The first step is to calculate for each geometry independently the location of its centroid relative or measured from A, and then we will combine them in the moment equation. So let's take for example the triangle. The centroid of triangle measured from A is given from the formula is 2 over 3 multiplied by the base, right? So 2 over 3 multiplied by the base. So it is 2 multiplied by 6 over 3 is going to give us 4, right? And since the triangle ends meets at A, so it's simply it's 4. Now for the rectangle, in fact, and I'll show you that, but since we are on this page, it's at center of that rectangle, which is measured from this end. If I measure it from that end, right, it's going to be from here to here, it's going to be 4, right? It's going to be 4. Therefore, from here to here, it's going to be 4 plus 6, so it's 10. So from here to all the way here, it's going to be 10. So now I know the centroid of the triangle and the centroid of the rectangle, both measured from A. Now for the equivalency to take place, or for the net, we know that the F resultant is simply combination of these two, which is 450 plus 120 is 1650, right? So this is 1650. It is somewhere, right? Pound, somewhere here, right? It should be somewhere over here. So where is it at, right? Where is this F resultant? That's the question. Okay, now I'm gonna go back to my notes. We have a distributed load called system A. We have already simplified these two distributed load into a resultant force of the triangle by FR1 FR1 is 450, located at x1 equal 4 feet, and FR2 from the rectangle, its total area under the curve is 120 or 1200 pound, 1200 pound, at location of 10 feet measured from the A point. The question is find the resultant force, which is WT, where WT is equal FR1 plus FR2, which is 1200 pound plus 450 pound. This is again 615 pound. WT located somewhere measured from A, and we donate that by XC, and we want to find that. So all these three systems are equivalent. Therefore, for these two systems to be equivalent, we said the moment equation should be, or the moment of this WT measured from A should be same as the moment of the two forces measured from A. Simple as that. So what do we get? We have moments of these two forces measured from A equal to the moment of force R1, which is, so I'm gonna go here, moment of A, I'm looking onto this, on this, equal moment of FR1. FR1 is distance, which is 4 by its magnitude 450. This is gonna give me the moment of R1 plus, and this is again, I'm using the right hand rule, so this is negative, so I'll put negative here, it doesn't matter, plus the moment of FR2, which is simply the distance from A multiplied by the magnitude 1200, and again this is negative. This is must be equal to the moment of WT, which is location, which we don't know where it is at, multiplied by the total, and the total WT here is 1650, right? 1650 pound, and this is negative, again right hand rule, and I go down. So we have all the negative will go, so XC is simply equal to 4 by 450 plus 10 by 1200 over the total force, and that's gonna give us 8.36. So if you're wondering how this equation came, we just discussed that on the notes. So with this, I will conclude the chapter 4. Next time we meet on Thursday, we'll start the chapter 5. I know the exam supposedly is in October 8th. I will discuss, the new date for the exam, especially after we cover some material in chapter 5.